6.4, I'm going to try and get this video in one part, so try and beat the 30-minute mark. This is the higher all questions paper for the space topic. Formula sheet, I'm going to stick down by here because I think we'll need it on the last question. Again, I'm just going to go straight to the question. Describe and explain the remaining observable stages in the life cycle of this type of star. I'm not going to say that because I don't know how to say it, but basically, if you just glance here, it's a 22nd brightest star visible from the Earth. It's 1,090 light years away. It's got a temperature of 42,000-ish, 22 times bigger than the Sun. All right, so the stages in the life cycle of this, it's a big star, okay? It's 22 times the size of the Sun, so I'm going to get from that it's a big star. So initially, the star is fusing hydrogen. This is when it's stable, okay? So maybe I could have gone a step further and said a star comes together by the formation of gas and dust, and then the gravity, and then it becomes a protostar, and then it's going to start burning hydrogen. But I've gone from here because it's just asking me about the life cycle here. So if it's fusing hydrogen, so all stars, even the small ones, fuse hydrogens when they're stable. It's stable because the forces of gravity and the radiation pressure going outward, so inward force of gravity, outward force of gas or radiation pressure, they're equal and opposite. Just like Newton's third law, equal and opposite. Once the hydrogen starts to run out, helium starts to fuse. So that is where the radiation pressure now is bigger than the inward force. So it's going to get bigger. This star is going to go to the next stage. In this case, it's going to be a supergiant. But if it was a star like ours, it's just going to go, it's just called a red giant. Star starts to expand and the outer layers start to cool. The star becomes a supergiant, or red supergiant. It gets hotter inside, but cooler on the outside. Fusion of heavy elements occur in the core. So the heavy elements like iron and copper and all those and everything, pretty carbon, everything that we're made of happens inside the center of that core of the star at this point when it's burning helium. Did I say that? Starts hydrogen, starts helium, yes. And then once fusion stops, the star will collapse and it'll explode into a supernova. And this is where it scatters pretty much all of its materials that it's been making inside the core out into space. And then the core contracts and cools, it's either going to become a neutron star where the star's not quite big enough to crush those neutrons, so we call it a neutron star. It crushes everything else, like protons, electrons. Or it becomes a black hole where it is heavy enough, it is big enough to crush those neutrons as well. And nothing can escape that, not even light. Describe the formation of our solar system. So clouds of dust and gas again, and heavier elements that's just been ejected from that supernova. They collapse under gravity and they start forming planets and the Sun. So that's our solar system. So this diagram here is called a Hertzsprung-Russell diagram. And basically on the side, it goes up, you can see to the power of, it's getting less there, and then more here. So the power of 2, 3, 4, 5. So this is luminosity. Luminosity is different from brightness in the way that luminosity takes into account the size of the star and how bright it is. So if you look at a star, you don't know how far it is away. Therefore, you don't really know how big that star is compared to its brightness. So they use this luminosity, it's in solar units, because they just, it could be a star that's far away yet really bright. But then you could have a star that's really close and not that bright, or the same brightness, but obviously the luminosity on that further star is going to be brighter because you can see it further away compared to the closer one. And then this scale, you've got to be careful on the bottom because it goes backwards, the scale. You'd expect as X increases, Y increases and all that at a decreasing rate there. It's not the case here because it starts off with the temperature's really hot, increasing temperature, and then you've got decrease in temperature this way. So, in fact, the relationship here, as X now increases, so Y increases as well. So you've got this. This is called the main sequence. This is where the majority of the stars lie. But then you get the odd couple of anomalies, like the white dwarfs are going to land up down here, where they're hotter but smaller. And then you've got these red giants here, which are cooler. Remember we talked about that outer layer being cooler. But the luminosity is really, I mean, because it's a big star then, it's like the luminosity is going to be quite bright. So these couple don't follow the trend. And that is basically the Hertzsprung-Russell diagram. It's no big deal to it. Okay, another a star I can't say. It looks like Spicer, I don't know, or Spica, whatever. It's a very large star. It's approximately 10 times the mass of our sun, so it's going to be a big one. Explain in terms of forces why it's currently stable, why it's in the main sequence star. So we can actually find where it is. Let's have a look. I'm looking now. You can probably see it before me. Ah, there it is. Look, right up here. Okay, so it's lying in the main sequence. Well, like I said, gravitational force and radiation pressure are balanced. So the gravitational force, inward force, radiation pressure, outward force, they're all balanced. State what this means, what a light year. This is like the half-life question. So it takes, so light from this star will take 260 years to reach Earth. So a light year is the amount of time it takes light to reach the Earth. And in this case, it's 261 years. And then part B, the sun is also a main sequence star. Explain in terms of forces reaction why the sun's properties shown on the HR diagram. Very similar to the last question now. I'm going to be talking about the properties. I'm going to be talking about reactions. And I'm going to talk about the forces. So in terms of properties, it's currently a main sequence. And then it's going to become a red giant. So it's going to move. It's going to move this way, okay, towards those red giants, and then it's going to collapse and become a white dwarf. So it's going to go up and then down. So I've talked about it's going to become larger. It's going to become a lower temperature. It's going to be redder, and then it's going to become smaller, higher temperature, whiter, and dimmer. And all that you can kind of get from the graph there. Reactions. Well, when it's a main sequence star, it's burning, it's fusing hydrogen. And when that stops, it's going to start fusing helium when it becomes a red giant. And then when helium stops fusion, there's no more and becomes a white dwarf. So that's your kind of 3 stages there. In terms of forces, when it's a main sequence star, forces are balanced. So the radiation pressure is balanced. But then when it starts fusing helium, when it gets to a red or a super red giant, there's an unbalanced force where the radiation pressure becomes more than the gravitational pressure. And then so I've said white dwarf there, the gas radiation pressure decreases when fusion stops, so it's gonna shrink. And then I've said end of red giant phase, outward forces cause outer layers to blow away, contributing to planetary nebula, leaving hotter core. But I think I've pretty much covered it all in there. You're gonna, from 6 marks, be very surprised if you can't pull 3, even 4 out of that. Just knowing what you know about the life cycle of a star. So main sequence, burning hydrogen, red giant burning helium, white dwarf there. It's when everything runs out, all the gas runs out. And it's the same in a big star as well. You just get that supernova. So let's bring this one up. This is our solar system made up of 8 planets, blah, blah, blah. Some information. Okay, the graph shows the orbital speed of the planets changes with their distance, the distance here from the sun. So first question, what is the orbital speed of Saturn? Well, let's have a look. So the distance from the sun of Saturn is 14. So I'm going to go, my mean distance from the sun there is 14. I'm going to bring it across. Watch your scale because it's going up in 0.5s. And then if I bring that back, it's going to be 3 there. So my answer is 3 times 10, that should be to the power 8 there, because it's times 10 to the power 8 there. Okay, so a little mistake by me. In fact, I'm going to write that in right now. There it is, to the power 8. Lovely. What's my next question? So I'm going to leave that out because I'm probably going to need it. Let's shift that up there. A dwarf planet is 700 kilometers in diameter, right? Orbital speed of 5.8, okay, and it travels 2.67 times 10 to the power 9, making one orbit of the sun. Use your graph to find the distance from the sun. So remember now, this graph, there's distance from the sun. I need my speed for this. So my speed was 5.8 times 10 to the power 8. So 5.8, so these go up now in, so halfway between is going to be 5, therefore they're going to go up in 0.2s. So that's going to be 5.8, bring it back down. That's rough, well, it is 4.5 there, 4.5. So that's my answer, 4.5 times 10 to the power 8. Obviously, I've done it there that time. I've stuck my to the power 8 in. Be careful here. A common mistake here is just to write 4.5 to the power 8. But it's 4.5 times 10 to the 8 there. Use the equation time, distance, speed of distance, speed, time, to calculate the orbit time. Well, here's your orbit by here. That's the distance. The speed you've got here. So I'm just going to, it's quite a quick calculation for 2 marks, considering it's on a higher paper. And that's going to give me 4.6 years. Estimate the mean temperature. Show your workings and how you got it. So for 2 marks, to estimate the temperature, I know that it is, the distance is 4.5 from here. Okay. So 4.5 is going to lie within within this range. So between 2.25 and 7.8. So it's going to be somewhere in there. Therefore, I can estimate my surface temperature. It's going to be anywhere between minus 22 and minus 149. So I've just given minus 90. Just try to get it in the middle there. State 2 reasons why this planet, why this star takes longer than Earth, or this planet actually takes longer than Earth to complete one orbit of the sun. Well, it's got a greater distance to travel in one orbit, and the speed is less than the Earth. So, and you can also say the gravitational attraction is less because it's further away. And how do we know that? Because we can get all the information from here. Look, so there's all your Earth information, and then here's all your information for this planet. I'm gonna go out on a limb here and say Ceres, who knows how these planets. I am not into astronomy, so please forgive me. Hope you got something out of that, and enjoy.